Now, we come to an example for cable-stayed bridges with a steel beam, and I have chosen the Strelasund bridge, which is the new bridge to the island of Rügen. We were checking engineers for that, so we were involved, and I have the pictures, which is always the problem, how to get, that's why I have chosen it. And it is a modern cable-stayed steel bridge which shows all the latest items. Here we see an aerial view. It's a very long bridge, 5 kilometers, from the mainland across an island here to the island of Rügen. There is an existing bridge, which is a bascule bridge, but because of fairly frequent openings for ships, long traffic queues built up. And so a high level bridge, which does not interfere with the ship traffic, was planned. Initial investigations for a main span of 200 meters required by ship traffic was done for a major arch, was done for a continuous girder, and for a cable-stayed bridge. And one of the criteria was the area of elevation, the area you could see when you look against the bridge. And naturally, the cable-stayed bridge, as the most slender one, had the smallest area to disturb, so to say, the landscape when you look against it. A cable-stayed bridge was chosen to take account of the maritime atmosphere at the Baltic Sea as an architectural feature. All the pier and tower legs were shaped like a drop of water. I think the proper word is they were tear-shaped, all of them, steel or concrete. Now, the bridge has one tower only, 198, 200 is good enough for bridge work, I would say, 200 meter height main span and about 126 meter side span, a little short for perfect balance, but of course there were buildings and other restraints, so that's what it had to be. And we see here the bridge. I've sailed underneath several times and have seen it this way, and it looks really very nice. So whenever you should have a chance, go there by boat, by a public outing boat or something, go underneath. It looks very nice. We have, of course, you see that without mentioning the harp arrangement of stay cables, which is aesthetically preferable because we don't have visual intersections from a skew view. It takes a little bit more material. In the calculation examples in Lection 5, I have an example. I show how the forces run in a harp system, but that's not significant. It looks quite beautiful. So whenever you can do it in a harp shape, do it. So that's how the towers then look. It's all one vertical cable plane. The beam was partly aerodynamically shaped, but not more than this. It's easier to make these straight plates than if you have curved ones, and that was good enough for the wind climate there. I mentioned the side span is a little bit short. If you calculate my rule of thumb, 40% should be the side span, then this is a little short. So we have rather heavy, strong uplift forces. To counteract these, in the side span, especially around the anchorage area, we use some concrete in the bottom slab as additional weight, as a kentledge. Also, 50 meters above sea, there were all sorts of careful investigations to prevent lorries or trucks from overturning and falling into the sea. And an unusual design was developed, unusual for Germany. We have here the regular steel barriers which we find on all Autobahnen. But in addition, we have two strong ties higher up to hold back lorries. And in addition, we have a very substantial pedestrian railing at the outside. Still, there is this problem, especially above the sea. We have that Severn Bridge in London. I could give a whole lecture on that problem and what to do, is that we have transverse wind on high cars, I call it, especially if they are unloaded and, campers, trailers. They are light, they are susceptible to overturning, but also trucks, high trucks unloaded, can be turned over. There are various solutions, and for the Strelasund Bridge, the following was done. You see, this is in transverse wind, the cross-section, and the more red the color becomes here, the higher the wind speed. And you see rather, and a truck goes about up to here, it's in the region, the upper region of the truck, still comes high winds. And so if we make wind shields in some way, then we lift up the location of the higher wind speed, we shield the trucks from the wind transversely, and that's what was done. In actual fact, it was decided to fill the openings of the traffic railing with glass cladding, so that's permeable for air and serves as a wind shield, these pedestrian railings also. Now, construction was, I would say, fairly typical. We start here with the approach bridges. The side span, we start here with one with an auxiliary pier, go back, use on land a crawler crane, here a floating crane. Then we come back, complete the side span, install the tower free cantilevering over the main span until we reach the second side span and close that. I'll give you that in some detail. During these free cantilevering of the main span construction, we have always the situation, which I explained you in some detail for the Mannheim North Bridge, that when we stress the new cable before the next element is on, the beam is pulled up. When, for the same situation, we then put on the new section without the additional cable, it goes down, up and down. And here you see, for example, if you look on the same color, up and down, or red, up and down, it's after cable stressing and after installation of the new element. Very, very typical. That's, of course, all part of the construction engineering, and it's listed in the construction manual, where you can check whether you are okay. Now, substructure, bore piles, the equipment on barge. In actual fact, it was a catamaran. In this case, two boats connected with a platform. And we have the two types of concrete piers. We have the tower for the cable-stayed bridge, concrete up to here, then a steel beam on top. We have the hold-down pier at the end, the side span of the cable-stayed bridge, where we tie down the forces, and we have the regular piers for the long, long, long approach bridges. We see here the side span piers cast simultaneously, and this is the beginning of the tower concrete piers underneath the beam with sliding forms. A look into the forms, you recognize again the tear-shaped cross-section we have on all piers as an architectural feature. I don't think the bridge would blow away if we would have used square piles, but it's an architectural feature. It's nice, it's interesting. So, now we said approach bridges. We built them from steel fabricated lengths, which are floated in generally, lifted up by a floating crane and placed. Now this is, maybe I go just back a second, I'm not sure about the number. We are now at the position here, we have all the substructure built, and we now install this, go back and do this. And then we go on. And that's what I'm going to show you now. Here. This is the first side span piece, and it was floated in to the side. It was here, then it's not floated, it's on land. I'm sorry, it's a crawler crane, and transported here with heavy duty rollers, lifted with a crane, and then moved over into the final position. It had to be lifted laterally, not in the center line because you couldn't get to it there. Laterally and shift. Quite an involved situation. And it partly was done by night because the existing road to Rügen had to be closed partly for lifting the elements, so it was done at night, partly. And here now we have reached, the side span is so far installed, the approach spans, we come to the side span. Here is a little diagram giving us an idea what we have to consider with the floating cranes. We have three parameters. First of all, we have the boom length, which can be short, medium, long. Then we have the inclination of the boom. The boom can be nearly vertical and it can be nearly flat. And thirdly, depending on those two, we have the permissible load, depending whether you are short or long boom on your inclination. And we see it here in this diagram. When we have the short boom and little inclination, we can lift 500 tons. Can you read it there? Otherwise you have to believe me. The figure is 500 tons here. And if we have the longest boom with the flattest angle, this permissible load goes down to 60 tons. So it's always a little puzzle if you have these great heights and distances and so on, how to use your crane. Then you go closer, you can put more load on, but you may not reach where you want. So if you reach enough, you cannot put on enough load. Sometimes you have to use two cranes. So these three parameters are sometimes a little tricky to maneuver. Naturally, if you use two cranes, then you have a big problem. If one crane operator doesn't look up and the two can touch, they can run into one another. That's all happened. And so one always tries to have cranes far enough spaced that they cannot touch, even if somebody isn't alert. So all sorts of tricky things. Now here, the long part for the side span is transported to the side by ship, and lift it up. Now in this case, the one floating crane couldn't do it, so here we come from shore. We have here a lifting, hydraulic lifting equipment, plus on the other side we have the floating crane to get the thing up. And in addition, here now with this lifting equipment we cannot lift laterally, goes without saying. But on the other hand, this in the later stage had to go over the pier. So it had to be lifted, inclined, and slide the thing in. So you don't like to do it. You don't like to lift with inclined ropes. You always try to lift just with vertical ropes, and with inclined ropes, when you have to pull, one doesn't like to do it. It was necessary here, but it's a little tricky. Anyway, so it's being lifted up, and here now we are high enough to slide it over the pier here, and so we can take out the inclination. It was quite an operation. Don't forget, people on site have to be very ingenious. We normally just work on shift the papers left and right, but on site they have to do it, and it's a tricky job, I tell you. Now, we have the approach span in place. We start tower construction. The tower pieces were also prefabricated with heavy-duty rollers, pulled on site, put on a barge, and lifted with the same floating crane. And for good measure, the first piece of superstructure was already welded to the bottom piece of the tower. We have here the concrete pier, I told you. We have here the approach span, which the inclination, which slid in. And now we come with the first piece of the tower beam, put it on here. And then once this is in place, we lift the other ones in and weld them together. Of course, everything was nicely investigated by Finite Element that it works. We see again the tier shape here of our tower, and finally we are up. The tower, as we remember, we have a concrete pier here, we have a steel tower here, so in between we have a bearing, which is a rather heavy one, very heavy loads, heavy horizontal forces from wind transversely, heavy longitudinal forces, e.g. from braking, fixed, of course, longitudinally and transversely, which ended up in a neopod bearing of 6.5 tons weight, substantial one. Now, we are back to the initial installment of the tower. You remember, this I showed you, slide it in, then we have here first tower piece with the first beam piece attached. Now we go on at the same time installing the tower and doing the free cantilevering, which gives us an additional tie, because we can only free cantilever further once the tower is high enough to install the cable. It saves, of course, construction time, but I have always tried to avoid it, because you have this additional connection between tower progress and beam progress. Once you have a holdback, you can't do that. And secondly, you have to work overhead. You have people working here, and you have people running here. And if they throw down a spanner or something, you may have a nasty accident. So due to these two reasons, I, with my bridges, have always avoided, if possible, this type of parallel building, the tower legs and the beam. But of course, as I say, it saves time. We see here, this is from the existing bridge, the free cantilevering, the new beam piece is being lifted by the tower crane and brought close. Now I will explain this, what you see here, type of two halves of a derrick in the next section. Because one shortcoming of floating cranes, there are at least two shortcomings of floating cranes instead of using derricks on the beam. The first is, once there is somewhere a ship in distress, may go under or something, off the floating cranes are. You cannot keep them on site if some emergency ship needs them. Off they go, and you can never forsake. And secondly, when you have an element hanging in a tower crane, because of regular little wind conditions, it's not precisely still. It moves a little bit. So, in order to connect the new piece to the old and weld it, you cannot have it hanging in a tower crane, in a floating crane. You can have it hanging in an erection derrick resting on the deck. That works. So if you use a floating crane, you have to have an intermediate fixing device. And that is indicated here in two halves, and I show you here. On the new element, you have this type of fixing frame, which is connected to the other half of the fixing crane, tied back to the already erected beam. And so the floating crane takes it up. You connect the two auxiliary frames to align the beam and have it hold it still, that it doesn't work, and only then you can weld. So you need an additional step. And here we see the situation. The new beam section is aligned or hung into this auxiliary derrick, and here we have this protective tent under which we weld the new section to the old. So we've done the free cantilevering of the main span. We go on installing the elements for the side span. A view into the steel beam. We see here the troughs of the orthotropic deck. Up here, this is a little cross girder. This is a cross girder. Up here is the roadway steel. We have the troughs with cutouts running through the cross girders, and we have here the bottom, the concreted. This is in the region of the hold down pier, where we have this ballast concrete installed, I showed you earlier. So we don't see the steel bottom flange, but we see the concrete. But of course we have the internal stiffeners here. Always has been a problem to attach the wearing surface properly to steel deck. That was for a long time a shortcoming of orthotropic decks, and this is the solution of today. We have here the cross, we have the top plate, 14 millimeters today. We have the trough, 300 millimeter distance, and we have then various layers of different types of asphaltic concrete. We have a prepared steel surface, we have some sort of glue mastics to stick it, and that works. There are, since several years, rules in the codes to somewhat prevent that we have hard spots, say by longitudinal girders or cross girders, in the support of the plate here, because when you have a hard spot, it deflects under a wheel load, but does not here, you have a sharp bend. And the problem always was the asphaltic concrete sometimes lifted off the steel for many years. And by making the elasticity of the supports within the orthotropic deck, one tries to avoid that. Of course, there is better material. The other way, very early on, was that you used shear studs on the deck and cast concrete onto it, or zigzag plates and things like that. It was a long, tedious process over many years, but this is currently the state of the art. Now, cable installation, you should already know all about it. I've told you. This is now just to show you that it works. For an example, we use parallel strand cables. This picture you've seen already. The 0.6-inch parallel strands run through an end plate where they are anchored with wedges, and there's a PE pipe around, and the strands are individually coated with a PE cover plus grease. They're called monostrands. You will hopefully recall that from one of the last lectures. Okay, we pull up. Now, parallel strand cables are fabricated on site. The individual parts, PE pipe, strands, anchorage parts, come on site, and they are assembled in place. So we don't need to transport heavy units. Lifting up of the PE pipe, then once the PE pipe is up, hangs in the first strand, we use a so-called shuttle, which is a connection, you remember, huh? The connection between the new strand and a pull cable to pull it up. Here we have quite some strands already installed. We have then on top at the passive anchorage, we have the pre-wedging. We try to hammer in the wedges so the strands cannot slip. At this stage, there's very low or none stress on the strand, so the wedges, when you stress, may slip, so you have to pre-wedge them, either here with a hammer, or you can use more sophisticated hydraulic equipment, but the same effect, pre-wedged in place. The anchorage at the beam, the individual strands are pulled through, and then you remember one beauty of this system is we stress the individual strands by small jacks, which one person can carry, and not the whole cable with these ton jacks which you use where you use some lifting equipment. Very briefly, again, I told you isotensioning is called by DNV. VSL, I think, has another. But the thing is, we install the first cable with the first strand with a pre-calculated, I say, overstress. And then you put in additional strands, like here, and then, of course, when you put in an additional strand, the load on the first strand is slightly reduced, and so on and so on. And you do it like this, that you stress every new strand in such way that all strands, the before one and this one, have the same stress. And if you started with the wrong stress, at the end, you end up all uniform and right. And it shows here the stress in each of the strands. It goes down, 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 down. This is first, we target on 70% in the first go, on 70% of the desired stress. There we have quite some sag to take out. And then we do it in a second process. First process, there are some uncertainties to pull straight the strand and all that. But with 70%, the strands are virtually straight. They are in position. They then behave as an elastic member. So when we then stress from 70% to 100%, then we have, of course, the force stresses still go down, but we do not have this curvature here, but it behaves like, at 70%, it behaves like a straight element. And here we have always the actual and the measured, and you see it's all very close. Otherwise they wouldn't have published this graph. And here is a plus minus 2.5%, which would have been acceptable as a deviation. But this looks perfect. Hard to believe that it is a real result on site, but it illustrates it very nicely. Okay, these are the cables finally installed at the beam. And as for many bridges, we have I've summarized that under instrumentation, but it's actually two parts. The first part here is the measuring of the bridge during the final steps of construction to make sure we are there. And then the second step is, once the bridge is opened, we continuously monitor it. So here we see again a beautiful comparison between actual and theoretical values. The level of the beam, we are dead on. Beautiful. And then the other good indicator of correct geometry I mentioned to you before are the towers. The towers are indicators, 100 meters high or higher, and they are very sensitive. If something is wrong with the cable lengths or loads, with this long indicator you can very well measure it. And we see here the deviation of the tower from the vertical. I mean, in principle, the thing at this stage was supposed to be inclined. It's not a mistake. But we see here also very little deviation, and the same here. So we check the beam geometry, we check the tower geometry, and now in the final stage, we instrument whatever can be instrumented. Of course, we measure the wind, we measure the cable vibrations, we measure in accordance with the traffic load, the vibrations of the beam, whatever you can. Then, of course, there was done a statical load test. You run over, 20, 30 years ago, we normally used American trucks. The Americans were always happy to do something with their trucks, and they came and put on 30 heavy trucks or so, I don't know. So today I think it's more done with other heavy vehicles. Anyway, we calculate the deformation, put the vehicles on, and measure that. So all sorts of things. We measure the movement of the expansion joints, and all that is done. It's all very nice, but my experience is that it's extremely boring. Nothing ever happens. I have not seen, especially of course from concrete cable stayed bridges, but also from steel cable stayed bridges, that from exceptions anything happens. The bridge is just like a rock. So it's just straight lines, the output. You can sometimes have cable vibrations. I've shown you that in the cable lecture. But then you have to do something there, dampen them or so. But otherwise, well, it's nice to know what goes on with the bridge, and you get all sorts of oscillations and you can record them. But don't expect too much from them. A properly designed bridge doesn't move very much. Okay, now we look at the completed bridge. It is a beautiful bridge, also the light color given here to the cables as well, and to the edge beams. And of course it's important to have this curvature in. We don't want the curvature on the cable-stayed bridge. Let's go too far. There are one or two S-shaped in Japan or so. Yes, you can do it, but rather not. But the approaches should be curved also, because if you have a curved approach, when you come here, you can see the bridge. If you have straight approaches, you never see the bridge in total, because you can't look around. So just from the reason of showing the bridge to the public, one should have a long curve on both sides as an approach. Here we had, as always, if something for the TV cameras happened, those people who had nothing to do with the bridge are opening it. That's always the case. We had here, of course, our federal chancellor, Mrs. Merkel. This was the Federal Minister of Transportation at that time, the First Minister of the state of Mecklenburg, and I think this is the head of DEGIS, the state organization for these traffic projects, German Unity. But what was interesting at this day, the bridge was open for the public, and that, of course, you remember the Helgeland Bridge with the one and only traffic queue, and here we have the one and only pedestrian queue. The bridge was full pedestrians. It will never happen again during the life of the bridge. And that was a nice festivity for all people who went there. And most fittingly, we have a great fireworks to close an important opening. Thank you very much.